Hello. Küçük bir aradan sonra geri gelmiş olduk dostlar. Bir sonraki sunum son sürat başlıyor olacak. Barkın'ın sunumundan sonra biz şu anda da Barkın sunumundan sonra üçüncü konuşmacı olarak bir İngilizce sunumumuz var. Ben doğrudan konuşmacı ekranına şimdi sizleri geçiriyorum. Konuşmacı ekranı ve speakerların içerisinden de küçük bir düzenleme yaptım. Ve hazırız. Can you hear me, man? Are you there?
Yeah, I'm here.
Let me check that your voice is loud and clear for the chat. People, can you please tell us that the voice and the loud is okay?
So just for a test run, my name is Usama,
Okay.
and excited to be at HackerConf.
Yeah, very nice. We are very happy to have you in the conference, man. So your voice is clear. We got the confirmation from the chat. You are ready to go.
All right, thank you very much, Mehmet. So as I just mentioned, my name is Usama Saqib, and today I will be presenting on a topic called Deep Dive into Binary Genetics, Detecting Code Reuse by CFG Analysis. So basically what I will be presenting in this talk is a system for performing code reuse detection. The meaning of code reuse detection is pretty self-explanatory. It's any method we can use to establish some kind of equivalence between two different programs. It has numerous use cases, ranging from plagiarism detection to patch detection. Other applications may consist of forming knowledge bases for recurring functions for reverse engineers. But at TrapMine, of course, we're looking into this with regards to its application in malware reverse engineering and malware detection. The main outline of this talk will be as follows. It can be divided into three main sections. The first sections, I will give a general overview of the system. The point of this is to contextualize the discussion later on in the presentation. The second portion describes the details of the algorithms and how they were implemented in our proof of concept. The third system discusses possible challenges a system such as this may face and some possible avenues for improving the performance and the accuracy. All right, so let's begin with the high-level system overview. So whenever we're faced with a problem, I think it's always best to define a precise problem statement. And for our scenario, the problem statement goes something like this. We want to be able to detect if a function is similar to a database of known functions. Moreover, we want to put certain constraints on our system as well. So the first thing is that the system should be efficient. It's no use designing a system which at the minimum takes longer than manually reverse engineering the function. Ideally, it should be much, much faster than even that. We want the system to be robust. What I mean by this is that the system should generalize away from basic bytecode analysis techniques. It should be able to detect variants of a function and should not be fooled by techniques such as instruction reordering, register relabeling, which are common techniques used to generate metamorphic variants of malicious binaries. Finally, we want architecture independence. We want the system to be able to compare binaries across different architectures. As we will see later on, the condition also purchases us another very important advantage. Imposing this constraint allows us to solve the problem of dimensionality that may arise from dealing directly with huge instruction sets such as x86 and ARM. The problem of dimensionality refers to the issue that as the number of dimensions of your analysis space increases, the amount of data needed to achieve statistically sound results increases exponentially. So, if we're going to be comparing anything, we have to begin by defining how we will compare. For our case, we compare across two features. The first is the syntactic information. This is basically what kinds of instructions are inside the binary. Note that this feature does not understand what the instruction itself means, but only looks at if it is present. This will help us identify similar portions of code. The second feature, and this is very important, that we want to encode is the topological information. This will basically encode the control flow of the program. This feature comes closest to encoding the logic of the program itself, since the control flow represents the information flow. So as those of you who are experienced in reverse engineering or malware analysis might know, control flow graphs are a very common representation to represent binaries. A control flow graph encodes the information flow of a computer program. It is formed of basic blocks which refer to sequences of instruction without a branch. So for example, as you can see, each block has instructions which always end with a branch instruction. A branch instruction can be anything from jump to call instruction or return instruction. A robust similarity metric must encode this information somehow, since it defines what can be most closely regarded as the meaning of the function, the program. All right, let's briefly cover what techniques we'll be using in order to be able to solve our little challenge. So we know that the information we want to assess. This information is the syntactic information, the topographical information. We will use two techniques for evaluating this information so that we may form our decisions. The first is something called locality-sensitive hashing. This is a scheme for hashing similar items to the same value. The main idea is to provide a function which, given some similarity metric, will group the same items together. Note that the definition of similarity is up to us, and it can be defined as loosely or as tightly as we wish. A useful visualization to understand how locality-sensitive hashing works is to view it as something that sorts similar items into the same buckets. So, for example, in the diagram shown on the slide over here, the locality hashing scheme visualized sorts items of the same color into the same bucket. The second technique that we will be using is something called the Weisweiler-Lehman graph isomorphism. The name is pretty annoying to pronounce. Graph isomorphism is, so two graphs are said to be isomorphic if they have the same set of vertices that relate with each other in the same way. For our problem domain, two isomorphic control flow graphs represent the same flow of information, if all basic blocks are the same as well. Graph isomorphism is a computationally expensive procedure and is believed to be NP-complete. The Weisweiler-Lehman approach, on the other hand, is just a heuristic for determining if two graphs are likely to be isomorphic. It does this in linear time, which is ideal for us. Thus, this algorithm is an efficient alternative. For our purposes, this algorithm, with some added variations, works well enough to encode the topographical information. So, how will we go about achieving what we want to achieve? We combine the two techniques just listed in order to construct high-fidelity signatures for our functions. The aim is that these signatures can capture the nature of the function and are resistant against some general metamorphic schemes. Briefly, our system will go through the following procedures. We will label each basic block using a locality-sensitive hashing scheme. The scheme will give similar basic blocks the same signature, as I discussed. Effectively, we want the scheme to be resistant against common syntactic alteration schemes, such as instruction reordering, register renaming, etc. These labels will then be used to compute the Weisweiler-Lehman graph kernel for the function. We will discuss this kernel in detail later on. Intuitively, what we're trying to achieve by doing this is this kernel will give us a signature which is sensitive to the position of each basic block with respect to its neighbors. This is how we will go about encoding the topographical information. However, before we can begin to do any of these, we want to extract certain information from the raw binary. We need three things. We need to perform function discovery, which means we need to be able to extract or divide the binary up into functions. We need to perform control flow recovery, and we need to lift the disassembled binary to an intermediate representation. I will discuss briefly what intermediate representations are and why it is particularly important for our use case. Intermediate representations are commonly used in compilers. It is a state the compiler converts the code into for performing optimizations. We do this here for two main reasons. The first one, as I discussed in the previous slides, is to achieve architecture independence. Secondly, and more importantly, we do this so we don't have to deal with monstrous instruction sets such as x86 and ARM. Intermediate representations are widely used to reduce the complexity these instruction sets present. It is also widely used to perform decompilation. For example, IDA has its own IR language called microcode. Binary Ninja uses the aptly named Binary Ninja IL, and Ghidra uses something called P-code. Well, for performing the steps we just went over, function discovery, control flow recovery, and lifting to an intermediate representation, we will be using Ghidra. Ghidra is an open source reverse engineering framework released by the NSA. It is widely regarded to be at the same caliber as IDA Pro and its capabilities. The IR Ghidra uses consists of a total of 68 instructions. It covers all of the common instructions such as arithmetic, logic, floating point, and memory access instructions. So this is basically just a screenshot from Ghidra's P-code reference page. As you can see, it categorizes all of the common x86 instructions into one equivalent instructions, thus reducing the size of the instruction set that we have to deal with, and in which also reduces the complexity that we have to manage. All right, so what do we have so far? At this point, we have a binary divided into functions. Note that these functions may or may not be what the programmer actually intended. We use general compiler agnostic. Ghidra and other reverse engineering frameworks use compiler agnostic function discovery schemes, which basically try to perform some kind of clustering of the control flow graph. The main idea is that it's able to divide the binary into separate modules. Secondly, we have the CFGs, the control flow graphs for each of the functions. And finally, each basic block of the functions has been lifted to Ghidra's intermediate representation. This is great because we're in a position to perform our code reuse detection. In order to prepare our basic blocks for the hashing schemes, we need to perform a few procedures. We convert the basic blocks into a vector that counts each instance of the instruction in the basic block. We ignore instruction operands since they make our hashing scheme sensitive to factors that can easily be altered. This makes our scheme too sensitive, resulting in similar blocks receiving different hashes. We really want to avoid that. So what we end up with is a mapping between a basic block and a bag of words. The slide shows this transition from a basic block with the original instructions to the intermediate representation, and finally into a vector representing the number of occurrences of each instruction. One curiosity to note is that the Ghidra P-code is much more bloated as compared to the x86, instructions. This is because a lot of x86 instructions have implicit side effects such as setting system flags. On the other hand, each P-code instructions makes any state change explicit. As a result, equivalent Ghidra P-code spans more lines than the original assembly code. All right, so the bag of word which we formed for each basic block can be regarded as a vector. Recall that a vector is just an object with direction and some magnitude in space. The vector shown here is in 3-dimensional space. However, the vector constructed from our basic block exists in a 68-dimensional Hilbert space. The dimensions come from the number of unique P-code instructions. Each instruction forms one dimension for a total of 68 dimensions. A Hilbert space is just basically a generalization of the normal 3D Euclidean space, and it carries forward the rules of vector algebra and the rules of calculus. As I talked about earlier, locality-sensitive hashing scheme rely on some kind of buckets to sort items into. For our case, these buckets will be combinations of hyperplanes in our 68-dimensional vector space. A hyperplane is just a subspace with dimension 1 less than our ambient space, meaning the ambient space here being the space within which we are conducting our analysis. In this figure, the hyperplanes represented with the red lines divide the space into sections. Each section is assigned a signature, and all items in that section receive the same signature. The challenge for us now is to partition the space such that the similar items get the same signature. In other words, similar items should end up in the same sections. The effect we're looking for is to group the vectors of our basic blocks such that similar ones have the same position with respect to each of the hyperplanes. In order to do this, we first generate uniformly distributed hyperplanes in our space. We then come up with a hashing scheme that relates the position of our vector with each of the hyperplanes in our space. So briefly, our hashing scheme is as follows. We compute the inner product of each vector with each of the hyperplanes. From this, we can compute the cosine of the angle between the vector and the hyperplane. The sign of the cosine tells us which side of the hyperplane our vector is on. From here, we can establish a scheme where we have a hash with a 1 each time the sign is positive and a 0 each time it is negative. We can visualize our space to be partitioned into sections where the label of each section is determined by its position relative to the hyperplane. The vectors that end up in the same section therefore receive the same hash. Let's go over a brief example covering this so that we may understand what's happening better. In the graph represented over here, we're dealing with a two-dimensional vector space. The green arrow represents the vector of our basic blocks, and the rest of the three black arrows represent our hyperplanes. Since we have three hyperplanes, the hash we will compute will also have the size will be 3 bits long. So the first thing that we do is we compute the dot product of our basic block vector with the first hyperplane. Then we can compute the cosine theta, a cosine of the angle between the vector and the hyperplane. From 1, we can see that the dot product relates the cosine of the angle with the magnitudes of the vectors. So this is how we can get the cosine of the angle. Since the sign is positive, the first bit of the hash here is 1. We repeat this procedure again for the second hyperplane. In this case, the sign of the cosine of the angle is negative. Therefore, the second bit of the hash is 0. Finally, we do this for the final hyperplane. Again, the sign is negative, and the third bit of the hash is again 0. So what we end up with, excuse me. So what we end up with now is a hash for our basic block vector, which is 1, 0, 0. Any other basic block vector which relates to the three hyperplanes in the same way will also receive the hash of 1, 0, 0. So what we have so far is that each vector that we're dealing with is formed according to the number of unique instructions in the block. Our scheme therefore labels basic blocks such that similar basic blocks are grouped together. In doing so, we have encoded the first feature we discussed, which is the syntactic information of the function. This is the information that describes the function at the level of instructions. So we have some preliminary results about how well the scheme works. So our test yield promising results for the applicability of LSH. For basic blocks that are at least 90% similar, the LSH scheme hashes them equally with the probability ranging from 97 to 99%. For basic blocks that are at least 80% similar, the probability drastically goes down to the range of 35 to 45%. This is exactly what we want, since we need the probability of two dissimilar basic blocks being hashed to the same value to be very low. This reduction should not be linear. However, it should follow something like the S-curve that we show on the right of this slide. The hash size we use in our experiments was 68 bits. Smaller hash sizes can be made to work equally well with the addition of LSH amplification schemes. So we have been able to cover the first information that we wanted to encode. Now we can move on to the second one, which was the topographical information. This means that we want to encode the control flow of the function into our signature. It has been shown in various research that control flow information offers a very robust metric for comparing binaries. Including this will give us a signature that encodes the function's nature to a high degree of accuracy. For this purpose, we will use the Weisweiler-Leemans graph kernel. This is an extension of the Weisweiler-Leemans isomorphism test, which we will briefly discuss. So the test goes something like this. Given a graph with labeled nodes, we iterate over all of the nodes of the graph. When we're doing this, we concatenate the labels of each node with the labels of its neighbors. We continue these iterations until the list for two graphs differ. If they differ, we know that the graphs are likely to be non-isomorphic. However, if they do not differ, after a certain amount of iterations, the graph can likely be isomorphic. For our application, however, we use a slight variant of this algorithm. We will look at this variant in detail. For our examples here on, let's assume a few things. The instruction set that we will be dealing with in this example, suppose that it only consists of 4 instructions. Let's suppose that the vectorization of the basic blocks has the form as shown on the screen here, and the hash of this basic block is represented with the function application notation, which can be seen in the third point on the slide. So, for our LSH scheme, all the basic blocks in a function are labeled with a signature encoding their syntactic information. This is the first thing that we discussed. This is the first of the techniques that we discussed. So our algorithm begins with each basic block labeled with this hash. In the first iteration, we look at the neighbors of each basic block. We combine the vectors of all neighbors and recompute the label using LSH schemes. Note that combining the vector is basically like forming a new, bigger basic block, which includes all the instructions of its neighbors, and then computing the LSH scheme over it. Let's take a brief look at how this might work. So let's focus on the bottom right subtree of our control flow graph. For this, the root of this subtree has 3 neighbors. The first is the root of the control flow graph itself, and then the 2 children. As such, the new vector for this node is computed by pairwise adding the vectors of its 3 neighbors. The new hash is then computed over this vector. Both the children have only one neighbor, which is the root of this subtree. The new vector is just the vector of the parent plus the vector of the child. So if you focus on the slides on the screen, we can see that indeed the root of this subtree, the new hash for the root of this subtree is computed by first adding all of the hashes of its neighbors with its original hash. This new vector, the new hash is then computed by applying the LSH scheme over this new vector. In the second iteration, we repeat the same steps. The third hash of each basic block is computed by adding the vectors from iteration 1 to the vectors of its neighbors. In this iteration, only the root node of the CFG is changed, since this is the only one that receives new information. All other nodes receive the same vectors again, therefore the third hash is the same as the second hash. Finally, the hash of the whole function is the collection of all the hashes of its basic blocks. It is worthwhile to try and understand how this procedure encodes the topographical information of the CFG. Let's take a look at the root node of our control flow graph. The original hash is the one we compute over the basic block alone. The second hash is computed by adding the information of the 2 children. Therefore, in a different function, a node would have the same second hash only when the function has 3 basic blocks that have the same original hashes as these basic blocks, and which also connects with each other in the same way. As the algorithm iterates, we put tighter and tighter constraints on the relationship of the basic blocks. So in this example, the hash of 2 functions would be the same if the neighbors of the neighbors relate in the same way, meaning we've gone 2 levels down the subtree, therefore we're looking at how the neighbors of the neighbors are relating. In other words, each iteration builds a hash from a subtree of the depth of the current iteration. So in iteration number 2, from the perspective of the root node, we go 2 steps down into the graph and then look at how the neighbors in this area or subtree relate to each other. Using this information, we form the new hash. The final hash of this function encodes both the syntactic information of the function, which comes from the vectors of the basic blocks, which are in turn created from their constituent instructions, and it encodes the topographical information, which comes from combining the vectors of its nodes in the order in which the actual basic blocks relate to each other. So this is worth repeating. The reason that the final hash of the function encodes both the syntactic information and the topographical information is that the hash of the original basic block is formed from the vectors of its instructions, and the second function hashes are formed by combining the original vectors in the manner in which they relate in the original CFG and then recomputing the hash on them. So the hash that we compute after the application of the algorithm actually encodes how the basic blocks relate to each other. In a graph with the same basic blocks that actually relate to each other in a different manner, the final hashes would also be different. So now that we have the hash of the functions, we need a way of computing the similarity of the two functions given their hashes. In order to compute the similarity score of the functions, we use the Weisfeiler-Leibman subtree kernel. The formula for computing this kernel is as shown. What this basically states is that for each possible hash, we count the number of times that hash appears in our two functions. We then compute an inner product over this vector. This gives the similarity score of the function. So we can go over a brief example of how this kernel function computes the similarity score. So let's assume that we have two functions with the list of hashes as shown. We pairwise multiply each of the hashes and then add them up. The effect that this produces is that the inner product amplifies the presence of shared hashes and nullifies the effect of the absent one. So we can see how this happens. The function 1 has 3 instances of the first hash, and the function 2 has 1 instance of the first hash. Multiplying this amplifies the presence, the contribution of the score in the kernel. Whereas with the second hash in both of the functions, one of them has the hash occurs 0 times. Therefore, in the final product, the effect is nullified. So let's discuss the results for the final system briefly. We tested this approach over known sets of malware families. The tests have given positive results. However, such tests aren't enough to prove the efficacy of the system. In order to ensure that the system reliably detects similar functions, we must first create a database of known duplicate functions so that we may calculate an accuracy and precision score over them. This itself is not a trivial process, and it's something that we're looking into doing at the moment. Once we're able to construct such a database, we'll have a more solid test results of how this system actually performs in detecting similar functions. So I believe we have a few minutes left. So that means we have time to go over some of the challenges a system like this may face and possible avenues for improvement. For the LSH, right now, the hyperplanes we generate are uniformly distributed in our vector space. Certain hyperplanes, for example, a hyperplane with all negative components, would always lie on one side of all possible basic block vectors. The reason for this is that we cannot have negative instruction counts. Therefore, a hyperplane with all negative components would relate to all possible basic blocks in the same way. Therefore, hyperplanes of such nature do not help encode any useful information. A possible improvement would be to generate hyperplanes with respect to the data bias, which would result in better space partitioning, and hopefully will give us even better results. So So one of the possible avenues of improvement is that right now, as we discussed, the basic block vectors are just counts of each of the instruction in the block. This count is an unordered set. However, we all know that in computer programs, the ordering of the instructions matter, though not always. We can replace this naive counting approach with something more sophisticated. For example, we can use Markov chains, which encode the probability with which one instruction follows the next. Such a model might be more appropriate for our use case. Finally, elicit schemes use and/or amplification to get better results. Further research into this might help improve our baseline results. For the Weisfeiler-Liebman algorithm, the improvements suggested have to do with the improvements in the graph kernel. The current kernel computes using the inner product. This approach might be unreasonable since it increases the contribution of certain hashes when comparing a small function with a large function. A different kernel which avoids this will drastically improve the reliability of the score. Moreover, the kernel gives equal weights to all hashes. However, as we saw earlier, hashes computed later on in the iteration encode stronger topological information. Therefore, a scheme that prioritizes these hashes would definitely be better in giving us more reliable results. Secondly, we can improve the system with regards to how we compute the similarity score. At the moment, the similarity score is not normalized. As such, it has no range. Normalizing it will, so this means that we have no way of comparing when one similarity score is bigger than the other. This is because when comparing two very large functions, we may get a high similarity score as compared to when comparing two small functions, even though the two small functions might share a higher similarity than the larger functions. This problem can be very easily solved by normalizing our similarity score. This will allow us to compare the scores within a range. Yeah, so normalization will help mitigate this problem. So for those of you interested and who would like to review these slides later on, and for those of you who would like to take a look at our proof of concept, we will be releasing both of these things. Keep an eye out on TrapMind's Twitter page, where we will provide updated information about how you can access both of these things. We hopefully will also provide a GitHub link to the proof of concept as well. So this is the references that I used for this research, and that's about it. Thank you, and I'll welcome any questions.
Hey man, thank you very much for this beautiful presentation. I'm looking for the chat right now to be able to see the questions. If we have any, people are clapping their hands. You know,